Swayam Prabha. Digital India. Educated India.
Okay, so you write it on the board. You write on the board and explain to the entire class. There is some confusion. So Soundarya will explain to you. Just look at how this expression is derived. Now you have some idea got it? You can erase this part. Yeah. Yeah. Yes. Clear? Okay. All right. So in photophysics, normally quantum field of fluorescence, if you want to calculate, all that you need is two different lifetimes. One is the fluorescence lifetime, another one is the radiative lifetime. If that is given, you can find out the quantum field of fluorescence, which is the efficiency of the fluorescence. Because in the expression that you learned in school, number of photons, who is going to count? It's not possible experimentally. Okay, so that definition is almost useless in the sense that how do we find out quantum field? Whereas here, these are all experimentally determined quantities. So you can find out these lifetime values using an instrument, and you can use that one to find out the quantum field of emission. Okay, so far so good. Very nice. Now we are going to talk about another phenomena in photophysics which is used for many applications. For example, fluorescence based sensors, you must have heard about, like sensing some analytes, fluorescence technique is used, right? So many of these sensing applications are depending upon when you add an analyte, what happened to the fluorescence. If the fluorescence is getting decreased only for a particular analyte, you can use fluorescence to detect that. If A, B, C, D, E, F, G, so many things you are adding to a system, only when you are adding C, fluorescence is getting decreased. You can identify C, no? So this sensing application, a lot of fluorescence based techniques are available. So to this decrease in fluorescence, yesterday I think some of you have seen fluorometer, one batch. Yesterday you have seen the lab visit. You guys, UV, so there are maybe two equipments are there. One is UV spectrophotometer, another one is fluorimeter. I don't know whether which one you have seen. Fluorescence, they told you that this instrument is used to measure fluorescence. So that is called fluorimeter. Maybe pakatile there is another UV, because normally these two instruments are kept each other. Okay, so there is a UV visible absorption spectrophotometer which is used to measure the absorbance or absorption. Another one is for measuring the emission or fluorescence. So in emission fluorescence, the way that yesterday we found the steady state spectrum, right? There will be some a broad peak will come, depends upon the emission. Now imagine that you have that analyte C, where the analyte interact with the fluorophore. As a result, fluorescence is decreasing, right? So in the absence of C, this will be the emission steady state spectrum. In presence of C, maybe like this. What happens? Fluorescence is decreased. This phenomena is called quenching. Fluorescence quenching. What happens is, so we are again, our idea is to see how we can use the kinetics to determine quantitatively all these phenomena. Okay. So in this, going back to this diagram, just look at the T1. You have the T1 steady state expression and all. Now we are bringing another scenario where an analyte or another species is interacting with the excited state, and as a result the emission is decreasing. So pictorially I can represent it as, imagine that species, quenching species, we call it Q, quencher. The one that leads to quenching is a quencher. Okay. So by this line, I mean this arrow mark, what I am representing is, there is a quencher interacting to T1. It can interact with S1 also, both are excited state, no. But just for the time being, let us assume it is interacting with the T1. So there is one kind of probably a reaction. It can form a complex in the excited state. It can react in the excited state. Many possibilities are there, but T1 is interacting with the Q1. So one more channel, Kp is one channel, K dash ISC is one channel, another channel. Now there is another channel for dissipating T1, a quenching channel. What I want you to do, think and then write the steady state expression for T1 in the presence of quencher. You have an earlier case, in the absence of quencher, you have an expression. So now I am putting another scenario where I am adding a quencher, that quencher is reacting with the T1. How do you modify that chemical equation? One more term will come essentially. One more channel is opening. How do you incorporate it? Think about it. The question is clear. How to modify steady state expression for T1 in the presence of a quencher. So the term LHS il varuma, RHS il varuma? This new term that we are talking about, quencher, RHS dam varum. LHS means that KIAC into S1. That is only one, but there is nothing happening there. Vandadukku appuram quencher is interacting. So adu vandu RHS il varum. What term is the only thing you need to identify now. Ah, we need to modify that steady state expression for T1 in presence of a quencher. So when there is a quencher, assumption is that that quencher is interacting with the T1. Okay. So then T1 is decaying through that channel also. Just assume that it's a reaction between T1 and Q. So how do you incorporate that into the equation? That's the question. You're doing big things actually. This is how you do research. When research, the new scenario will come. You need to see how we can modify the existing equations to that. You can do it. Try. How do you do? So LHS, RHS, RHS, then the term will come, no? So that term is indicating like KF into T1, K dash ISC into T1, one more term for T1, right? And that involves Q1 also. And there will be, that's a process, there will be a rate constant for that process. See, rate of any process is rate constant into concentration. I already told all the answer now. Okay. You're 60% correct. In the sense that now don't directly modify. You write the RHS separately, all the terms coming. Then we will come back to this one. RHS you need to those terms will be there, no? KP that will be there, K dash ISC will be there. Then one more term you are now adding. That's separate Tanya, that term how to write you need to see. T1 will be there, Q will be there, then a rate constant will be there, right? Because it's a process. Every process has a rate constant. Then concentration. Rate constant into concentration is the rate. So how do you write it? How is it going here? T1. This is okay. And the RHS, whatever existing term will be there, right? Because those processes are also happening. What are the existing term? KP into that's already there. Now there will be one more term coming. Okay, then very good. Idile very difference in here all you putting T1, no? Why you are not putting T1 here? Only T1. But then Q is also there, no? That look at that figure. That's okay. Oh, that is only rate constant. Concentration term for where is that? This picture you have put there somewhere. In the picture, now you are putting. See, look at there. I am putting some concentration term there, no? That also affects, no? That process. Suppose I take more, that process becomes faster. So that term should also be included, no? Good. One more term is coming. Only thing is, okay. Suppose you write those terms separately, maybe here KP, K dash ISC, there's an expression, come back to it. This is, you're writing only Q. So that's what I was thinking. So what are the concentration that probably affect that process? Suppose I am taking very high Q, very low Q, that interaction will be different. So Q term should be there. Suppose I have a small amount of T1, large amount of T1. Do you think it will influence that process? The Q and T interaction. I have a small T, one case, some other case I have a large number of T1. That process will be getting affected or not? You take a stand, yes or no? affected. So T1 should be also there in that process. Okay, but then okay, fine. Now there will be a rate constant. No? Every process you put KP, you put K dash IC. So on the process, a rate constant. You put something KQ or some rate constant. Oh, KQ, small q. Oh. Right. Now, how do you get it? Okay, very nice, very nice. That's it. You can even, okay, this is a little complicated. We can probably use this expression, IA by, no, not IA, this one. Okay, this is also fine. This also. This can be the answer. Yeah, that's true. You can put that also, otherwise this is also fine. This is also fine, that's also fine. Both are correct. Okay. So, some of you go and write it. And explain how you arrive at it. You got it? KQ. One more term will be there. There will be a rate constant. So, what are the interaction? There is a Q, there is a T1. The concentration of Q, if it is different, will the process rate will be different or not? Differ. Suppose I change the concentration of T1, the process rate will be affected or not? Why not? I have small amount of T1, large amount of T1, Q1 is interacting. So do you think that these two scenarios, the rate will be the same or different? Because T1 is interacting, no? So the concentration matters. So in that expression, both T1 and Q terms will be there. And for that process, there will be a rate constant. Like a KP, K dash ISC, other processes also, there will be a rate constant. So you need a rate constant, concentrations of puncture, concentration of T1. That is the third channel. Got it? Yeah. Exactly. Top K dash ISC alone. S1 verify whether it is correct or not. Correct? Huh? Does it make sense? You understand how do you get it?
How
K?
come KF?
KF. She's coming. Make any small corrections, whatever you are identifying. KF is not there, KQ, right? So what is KQ? It is a quenching constant. That process, quenching, that is a process, there will be corresponding rate constant for that process, that is a quenching constant, right? KQ. And KQ, so see, this is a bimolecular reaction kind of thing. Q is one molecule, we can consider that. T1 is another molecule, quote unquote. So any bimolecular reaction rate expression will be some rate constant into A into B. We are assuming it is first order for the time being for this case. Okay. So that's how this expression is coming as KQ into Q into T. There is a T term also. What happened? That is a expression for T. That is a common term. Any clarification, doubts? What is unclear? Clear? Things are getting processed? No, I mean, are you getting confused or are you getting clarified? How this third term comes? You understand? Due to quenching process, T1 is getting annihilated or dissipated through one more channel. That is what we are adding, that third component. So here I can write as T1. Okay, this is T1 in presence of quencher. What was the expression for T1 in the absence of quencher? I put it as 0. What is that? Okay. That's all? Okay. Now, use T10 and T1. Get this expression. Get this expression from those two equations. T10 by T. Do some small rearrangement. Get that equation. Are you getting it? How this so far you understand what is? You got it? Okay. Some terms will likely to get cancelled, right? You take the fractions. Okay. So what happens? Some terms get cancelled. Okay. Now what is this k is equal to? This k represent what? I write only k there. Just rearrange carefully. You see, instead of writing this, you write one more time, one more step you write. See what are the terms remaining. K, Q, Q. All terms will get cancelled, only one term will get cancelled. That will go okay, but other, how do you cancel it? We cannot cancel this term. See, best thing is you write this another expression, this by this into this goes the top, Yes. On the step you write it, then it will be more clear. When you jump one step, sometimes we always make mistakes. Got it? Now one term get cancelled, no? Which one? KISC into S1. Okay. Now remaining is? Adu cancel panna mudiyuma? No. So how do you write it? Divided. Now you look at that equation where you want to arrive and see how to rearrange it. Got it? You're getting? Now you need to write. Are you writing? You're going to write on the board, okay? And to explain the class, how do you get it? You learn from them. Got it? Hmm. Hmm. Why do you know that? Why do you need? So this term get cancelled, right? So now you get okay, that so one divided by the other one, no? So T1, no, see T1 0 is on the top. That's a mistake you did. T1 is below. Okay. Correct. So now it becomes ulta, no? This A by B into D by C. So this which term get cancelled? This இது cancel முடியாது. That's what. So see, you need to write it as KISC into S1 divided by KP plus K dash ISC into this will be ulta. KP plus K dash ISC plus KQ into Q divided by KSC into S1. Now you can see this term and this term will get cancelled. And now this term will not get cancelled. The summation term, right? So what is remaining here, you write it as a second next step. Then you look at that what is to be proved and see how to reach there. Correct. Now I write only that K, right? So using this, what will be the expression? That K will be equal to KQ by KP plus K dash ISC. One more step is probably 1 by KP plus K dash ISC. What is that? 1 by KP plus K dash ISC. 1 by sigma K. The summation of two K's, no? What tau? Find out. Got it? All right. So what is that big K there? That K, 1 plus K into Q. What? After cancelling, we get this term, sir. Okay. Then by separating the denominator, you get it. Now I'm asking, what is that K in that equation? 1 plus K into Q. That K is equal to? Very nice. What is 1 by Kp plus K dash ISC? What is that? Tau? No. Got it? This K is equal to what? Big K. You get 1 by Kp plus K dash ISC. What is that? You ready? Ready? 1 minute. Okay. Other cancel பண்ண முடியாது. Still you can find out that relation. You write that only those two terms and look at that equation, see how you get it. You go and write it. No, you come. I will help you. Adu paravilla. My handwriting is even bad. Come here. Come. I will help you. This is his handwriting, no? Then you will recognize this. Other even difficult. Right from T10 to this expression onwards. Go ahead. You just do right hand side somewhere you can, or you can erase something. Got it? Very good. Okay, correct. What is this? Okay. So now 1 by this K means KQ by KP plus K dash ISC. What is 1 by KP plus K dash ISC? Very good. Correct தானே? Top தானே? So you can see that this excited state kinetics is very similar to ground state chemical kinetics. Whatever equation that we learn, you can use it and apply it to derive the equations. Good. So this K, whatever that K in the equation is nothing but KQ by KP plus K dash ISC, right? Now this I can write it as 1 plus KQ tau P, right, into Q. And this KQ tau P is the one that I have written as K. So this K is nothing but KQ into tau P. How does tau P comes? Anybody is getting confused why the tau P is coming? Tau P is what? Phosphorescence lifetime. Any lifetime is 1 by K. Phosphorescence lifetime means there are two processes in phosphorescence, Kp and K dash ISC. So 1 by Kp plus K dash ISC is equal to tau P, lifetime of the phosphorescence. So the advantage here is, see, concentration of T1 in the absence of quencher, in presence of quencher. Suppose you want to do an experiment in a laboratory. All that you do is you take a the phosphorescing material and you take the emission phosphorescence in presence and absence of a quencher, right? And you can then, you know the quencher concentration, you know the initial concentration of T1, you can use this to find out what you call KQ, which is the quenching constant. How effectively the analyte or the quencher quenches the phosphorescence emission. So instead of T1 0 and T1, can I write intensity in the absence of quencher divided by intensity in the presence of quencher, intensity of phosphorescence? Can I extend this equation to this format? Because concentration is proportional to intensity, right? So instead of concentration, I can just measure the intensity of the phosphorescence emission in presence and absence of the quencher, and I get a linear equation. This is like a y is equal to mx plus c equation, right? So graphically, if you want to analyze the quenching process, what you should do, this intensity ratio versus quencher concentration. Can you plot it using this equation? Plot the graph I0 by I versus quencher concentration. You learned mathematics, no, in BSc and all? Ah, it's a straight line equation, right? But draw it and then show me. Or if you write y is equal to mx plus c and you plot it, compare this equation to that equation. So this distance is this distance, y axis, what will be that equal to? But I am talking about this 0 to that intercept distance is that equation, you know, y is equal to mx plus c. That's one the mark. So in y is equal to mx plus c, where is c? C and other graph, how do you show it? Graph, how do you show the c? Y is equal to mx plus c, m is what? Slope. C is what? It's a constant, but it's correspond to the y intercept. So you need to show as a y intercept. That means this graph, this line will cut to the y axis, and the distance from the origin to that cut point is called the intercept, where the line cut the axis, where it intercepts. So, right. So here also you will get a similar graph, right? Because this is like y. Yes. C plus mx, that is a format it is written here, mx plus c. So you will get a graph like this. This will be your c, which is 1, intercept. So this graph will always cut to the y-axis at 1. Okay. What will be the slope? kq into tau p. So tau p is an experimental quantity. Lifetime, you can measure it. There are instruments. You know the intensity, you can measure it. Conjure is the analyte that you are adding into the system, that you can vary. So you know this, you know this, you know this. When you plot this graph from the slope, you can find out what? kq, which is the quenching constant. So how efficiently a quencher quenches that process, fluorescence or phosphorescence. In this case, we derived it for phosphorescence. How it is quenching the phosphorescence, you can determine quantitatively. A number you will get. Some 5 into 10 to the power of 3, something like that. Right? So that is the advantage for deriving this equation. There is a name for this equation. What is called? Stern-Volmer equation. So what you derived here is called Stern-Volmer equation. Stern-Volmer equation is used to analyze the quenching process so that you can get quantitative information about this quenching. Last exercise. No derivation. Okay, don't even write anything. I want you to only look at this final equation that you have done for phosphorescence quenching, and imagine that quenching is happening to the singlet stage. Okay, don't derive anything. I want you to write the final equation without deriving. Everything is same. Okay, whatever you have done for phosphorescence, you must be doing in the derivation for singlet also. How the final equation looks like because stem equation is same for both fluorescence and phosphorescence. So you write it, don't tell me, you write it, then I will ask you to tell. What will be the stem equation for fluorescence quenching? That's a question. Now, you don't show it to others, okay? Let them think. Okay, don't show to others. Everyone showed already? Okay. Okay, great. You can derive it, but this is what you're finally going to get it. Okay. Write it. Got it? You also got it? For fluorescence quenching, stem equation. Huh? You got it? What did you write there? Huh? You're doing. Is it together? Okay. Derive panna venda. Just by looking at that final equation, endha madri avunna guesswork. That's all. So the only difference is that top P becomes tau F. That is the only difference. If you derive it also, you will finally reach that lifetime of the singlet instead of lifetime of the triplet. So learned a lot of things, right? Good. So in this particular case, what you did is we derived it for assuming that this quencher is interacting in the excited state. This type of quenching, there is a name called dynamic quenching. Okay, because it's happening in as a result of dynamic collision between the quencher and the excited stage. Another type of quenching is called static quenching. Other one, the quencher will come in the ground state. So that scenario we did not even discuss. So in photophysical or any topic, there are enough topics to discuss days and days, months and months. But somewhere we need to stop, right? Good.
SwayamPrabha. Digital India. Educated India.